So we talked about interference when we talked about sound waves, right? But now we're going to look at it optically, and we're going to see that some of it's the same and some of it's different. But in order to look at interference in a more rigorous way, and or to look at it in terms of light, we're going to have to look at light as a wave. Okay? So we have here sort of our makeup. We saw some of this stuff when we looked at electromagnetic waves, right? Between the angle of incidence, reflection, and refraction. We can see these refracted waves. So a three-dimensional transmitting wave, which includes light and sound, can be predicted by Huygens principle, which is very important, all right? And it's going to state that on a wavefront, all points on a wavefront serve as point sources of spherical secondary wavelets. At a time t, the new position of the wavefront will be that of a surface tangent to the secondary wavelets. So what does that mean? Well, let's look here. This figure will make Huygens' principle, which is very subtle, make sense. There's a lot of stuff going on there. All right, so pick any point along the wave, and you can basically pick any point along this continuous wave, and you can say, ah, that's a small source of a now expanding wave. And you can see that the new position of the wave can be thought of as of each point being a source and then adding up and constructing to constantly create the new wave. Now, this is going to be important for understanding features of interference of light waves, because we'll be able to reflect some of these points and absorb some of them and let others transmit. So we can actually build structures that demonstrate this, okay? We can see that when in terms of refraction, right? Notice we have, look at each point along the wave. Only this point refracts along the wavefront, right? And then as soon as this one gets here, it's still traveling, but then it refracts and then adds up to sort of continue the line. And then you'll notice that this one later then refracts. So that's how you look at these. You sort of look at this line as each point sort of continually making up this new wavefront here, okay? And these curved parts are the spherical parts of the waves from each of these wavefronts. Another way to look at it in a more simplified version would be like this. All right, it always starts with blue. Let's do yellow. So say you had two of these points. So from each two of these points, you have a wave that sort of comes out and becomes bigger and bigger and bigger until it's so far away, it just looks like a plane wave. And you have the same thing here. You'll notice these start to cross until they'll eventually, if they're in phase, they'll add up and just can be a more intense wave with everything sort of adding. Or, you know, the intensity of both these dots can add up, and you'll notice when you add up all the points and they all superposition or add together, just like we saw sound waves do, you get a wave of the same intensity, because the intensity of this wave will be the sum of the intensity of the points from all the sources. Okay? So that's what we mean by wavefronts and points emanating from a wave. Okay? Now, we saw Snell's law, all right, before, which will give us that N1 sine theta, N2 sine theta 2. But now what we're going to do is we're going to relate the N to some of our wave properties, our index of refraction, and then we're going to be able to look at the wavelength change in the medium from being in a wavelength. So we'll notice that as we refract, the wavelength of the wave actually changes, right? You see that the wavelength is the distance between subsequent vertical bars here, right? So that's wavelength 1. Now you'll notice that we're pointing it out here that wavelength 1 is given in one medium, and we see a change in wavelength here in the other medium. Now, basically what we see is that in a medium, but what I should say here is that in a process like this, the color doesn't change, right? If you start with a red light, you still have a red light. So the frequency does not change, but the wavelength does. So that means that the speed of light in a material, so let's call it Cn, can be different, but must be less than equal to c, the speed of light. All right, the speed of light in the vacuum is the maximum speed limit of the universe, but you can slow down the speed of light in a material, and it's given by this equation here. So you can see here that c, or it's not what I want to say, v equals c over n. And so for n greater than 1, you can see that this condition is satisfied. All right? So we can calculate the new wavelength in terms of the original wavelength in the same way, right? So all you have to do is recall that lambda times the frequency equals the velocity or the speed of light, right? Equals c. So we can replace our c's and v's and things like that and get the f's to cancel and the c's to cancel us in algebra, and you will get this equation here, all right, which shows us how the wavelength of light will change in the medium. All right. So, questions on that so far? Okay, because we're going to extend this to one of the more famous experiments of all time, which is famously the double slit experiment, okay? But in order to understand the double slit experiment, we're going to have to look at diffraction in terms, or we're going to have to look at this, not refraction, but this process of diffraction. All right, so you can see that if you have a source, right, and I've shown you this a couple times, if you have a light source and you get far enough away from it, I really don't want, hold on. I just don't like this all highlighted, so I'll go back and I'll go forward. Okay, so what I tried to show you there before the pen took on a mind of its own is that if you have a source, as these waves get bigger, you'll notice if we cut them off, they start to look like plane waves. All right, so the curvature is just too big, and you can't tell that it's curving out anymore. All right, so basically you have incident plane waves, right? And you'll notice if you can set them through a slit that's on the order of the wavelength, you'll notice they have this wavelength spacing lambda, and the spacing here is given in terms of the wavelength. You'll notice that the closer you get to the wavelength, the more of a spherical aperture you make, right? Notice down here at part C, these are pretty curved. It's a pretty good source. Whereas here, a lot of the plane waves are just going through. You very quickly get a plane wave back again. I don't know, I can't make it to the same spacing that they had, but you know, what are you gonna do? So, let me see here. So the effect that occurs here is called diffraction, all right? And you'll notice that it has all entirely to do, like I said before, with the spacing, how much the spacing has to do with the wavelength, right? If you're too small, nothing gets through, right? Or very little gets through. If it's too big, the plane wave just keeps going through the hole. Why is this? I have this hand thing here. It's bothering me. Hold on. All right, let's. All right, this whole program is starting to drive me crazy. Now, Young's interference, or the double slit experiment, was important because it's not, we don't make it clear from teaching you physics this way, but the debate between whether light was a particle or a wave was raging very vigorously, with Newton saying it was a particle. Some of you might say, well, quantum mechanics tells us that light has particle-like properties. It does, but not in any way resembling the form Newton thought that light was a particle. And Young's experiment, double slit experiment, established the wave nature of light because only waves could behave this way. And so basically what he did was he created a series to take any sort of random wave, right, electromagnetic wave, send it through a single slit, and then these waves would refract on these two slits, and these would act as wave sources. And then what you would see is that part of the waves, you get what's called an interference pattern, right? Where you can see that parts of it are missing because not all the wave is going through. Remember, in order for the wave to propagate, everything has to add up to recreate the whole wave. If you're only getting part of the wave going through, only part of it transmits, and you only have this broken up line. What you see on this side to the right of your slide is interference from a laser, which we do in the lab, but we're not there. So, sorry. So, you'll notice that you have these maximums and minimums, right? And you can see this for yourself. And basically, this proves light is a wave because if light were not a wave, you would just expect two clumps that sort of meet in the middle, and you wouldn't see any of these outside interference patterns. And you can actually see interference patterns that dim all the way up and all the way down. There eventually comes a point where, you don't see much, but the wave nature of light puts it there, creates this pattern. So this is a clear result that if light were a particle, the way Newton thought of it anyway, you would expect something sort of bimodal like this, where the light just comes through and collects around here at the different angles it's incident on the plate with. Okay? But that's not what you see. You see this interference pattern. Now, much like we had with sound, we have similar constructions for interference. So you'll remember, if you remember from chapter 16, right? Delta L had to have conditions between two paths had to be some integer of the wavelength or half integer of the wavelength to create constructive or destructive interference. So does everyone remember what constructive interference was? Anyone want to give a little shout out there? What is constructive interference or destructive interference? Well, well, let me ask it a different way. Is constructive, that's not very helpful. Also not helpful physically. Let me ask you it this way. Is constructive interference the one where all the sound cancels out, or the one where they all add up? Constructive is the one where they all add up. So right. So with light, what would you expect to happen with constructive interference? Right, and destructive cancels. Brighter, good. So you'll notice that these points represent constructive interference, and these points represent destructive interference. And we can figure out the positions of them, or at least the maximum, where they're maximums, by employing sort of the same idea, where we have the distance between the slits. These are the distance between the halfway points of the slits, right? And then we draw these semi-parallel rays. Why do I call them semi-parallel? Because if you look at this picture, they look parallel. Mathematically, they cannot be parallel because they meet here at the screen. right? So they look parallel, but they're not quite. So we do a little bit of a game here. And essentially what we do here with this game is we make this triangle right here, and we have D, right? And we can look at this as the path length difference, D, or delta L. And so delta L will equal R2 minus R1, right? But because we have a triangle, we can also see that delta L will equal, if this is the hypotenuse, we can see that sine of theta, if this angle, for the angle theta in the triangle, we can see that sine of theta will be the opposite, which is equal to delta L. I'm just going to cross this out here, over that little d, right? And so this is just using trigonometry. So that implies that delta L equals d sine theta. So that's something easy to compute, right? And this is something hard to compute. So we'll always go with the easier one. So you'll notice that the conditions for maximum and minimum are the same as they were before, right? If you have your delta L, which is d sine theta in both of these, if it's equal to a wavelength or integer wavelength, that will give you a maximum. If it's equal to a half integer wavelength, that will give you a minimum. All right, destructive interference. And basically, if it's in between, and it's not really that interesting. We're interested in the maximum brightness and the minimum brightness. Those are the easiest to predict and to verify. Okay? So you'll notice they talk about the approximation here, in which they're quasi-parallel lines, right? Okay. So, questions, thoughts, anger? No, why are you angry, Douglas? Oh, okay. All right. So, moving on. We want to talk about interference in a double slit through a double slit aperture. So if the two light waves that meet at a point are to interfere perceptibly, that means if we can see it, both must have the same wavelength. Let me see, the same wavelength and the same phase difference between them must remain constant with time. That is, the waves must be coherent. This is why it's hard to see interference patterns with, say, a flashlight or a white light source, because there's a lot of different phases or lights in there. But with a laser light, it's pretty easy because the laser is coherent. All right. One way, I think the easiest way to understand coherence is that when you add intensities, you can't just add intensities. You know, intensity is usually the power squared. Adding intensities is sort of akin to doing something like this, right? You can't add a squared plus b squared does not equal a plus b squared, right? There's a cross term, or in here what would be a coherence term. Now, if you're incoherent, that cross term won't add much, and you add the two sources together, you just get the sum of the two. But you not only have the sum of the two sources, but if you maximize the coherence, that cross term, right, you can get another addition of 2 times the intensity, and you'll find that the intensity of the coherent beam is 4 times the initial intensity. But again, this happens only when coherence, when that phase difference doesn't change over time. It's a fixed phase difference. So you can see the intensity will be equal to 4 I naught times, for at any point, times cosine squared 1/2 phi, where phi is again here this 2 pi d over lambda sine phi part. So to really look at this, to get a sense of how the intensity works for a coherent source, I naught cosine squared of 2 pi d over lambda sine phi. All right? And if you look closely, you'll be able to see that you have d sine theta. That can be your change in path length. So you can get this in terms of that change in path length pretty easily. You'll notice they have a delta L over lambda part for maximum minimum. They show them. They do show them here. Okay, so you can get that intensity, but it's not a trivial function by any means. And again, you have to be in phase, have a constant phase relationship between them, have the same wavelength. Okay, so these are the things that are important to have coherent light sources. And again, a coherent light source, good example is a laser. Bad example, or a non-coherent light source, is your light up at the top of your ceiling. Okay? So, we already saw that. Interference from thin films. Thin film interference is sort of interesting. I'll let you read this while I talk, but basically with thin films are fascinating because you can often use like with bubbles, for instance, you can often use the colors to figure out, because you're seeing interference in the colors in thin films, you often can calculate the thickness of a bubble or something that you couldn't ordinarily measure by looking at the colors that come out of it. A good example of this is bubbles. If you look at giant bubbles and you see the colors changing, each color shows you the thickness of the part of the bubble you're looking at. And you'll notice that because the colors are changing rapidly, the thickness of the bubble is actually fairly unstable, which is why it pops. If you had the more stable the bubble, the less rapid those colors should change. So that's what I have to say about thin films. I'll let you look at that there. Now the last object, I do want to spend quite a bit of time on this one. And so this is the Michelson interferometer. So interferometers are critically important to the study of modern physics and things like quantum physics. In fact, my PhD is on a type of interferometer called the Sagnac interferometer. I didn't invent the Sagnac interferometer. I'm not even close. The Sagnac interferometer was developed in 1913, and I, virtually 100 years later, was still investigating very new effects of working with it. So there's a lot to look at when it comes to interferometers. The Michelson interferometer is famous not only for its measurements in quantum theory, but it's also the device that proved that we were not in a luminous aether, right? So again, you have to understand that there's a difference between sort of these science ideas people have and the fact that when you come up with an object like a luminous ether, or whatever it is, it has to have consequences, and you have to propose experiments. So all sorts of experiments were proposed by this the existence of this ether, and the most fundamental ones, or the best precision ones, were proposed to be done with this object called an interferometer. So let's talk about how an interferometer works. Okay, so the same conditions for interference have to be true, right? The path length difference has to be either a wavelength or a half wavelength off. Now here's where this gets interesting. So you have a source, all right? Now the source, I'll pick one color. They could have done this better, but they didn't. So we'll leave the first source in red, and we'll make the secondary source in blue. So you have this red here, right? So one of these will go, the path it takes goes along the mirror. It reflects back from the mirror, comes down here, and goes to the telescope. So that's path one. The red path right? This is usually a half silvered split mirror, so it's reflective on one side, not on the other. The other one goes up arm 1, through arm 2, and down into the telescope or the viewer to create the interference effect. Now, here's where this gets interesting. This mirror here is movable. This one is not. All right, this one is fixed, this one is movable. And you can actually create a system, the resolution is only limited by the wavelength of your source. So you actually get a half wavelength resolution in the frames with this instrument. So this allows you to make mechanical movements on the scale of half a wavelength of light, which is about 330 nanometers. And so you could measure differences like that. All you have to do to measure a path difference, you can make these bigger and interesting by placing something in one of the paths. So here you just have a movable mirror, right? But you can put a gas in here, you can put all sorts of stuff to change the path length difference and relate the interference to whatever it is you put in here, whether it's index of refraction or something like that. And you get really the basis behind the most precise measurement apparatus in physics, all right? And it's not just the Michelson interferometer. There's a ton of different devices based on interferometry. One of the more exciting ones, if you took Physics 1 from me, I asked you to shortly research gravity gradiometers to figure out how much precision you could get with little g. And so that uses the interference, and there's a lot of interferometry experience, not so much with light waves, but with quantum matter waves. And so matter wave interferometry, that's where I got my PhD in. That's an interesting field. Well, of course I think so. I got a PhD in it. And what we see there, though, with these gravity gradiometers is that you can use interference to actually look for small variations in the gravitational acceleration, down to about the 13th decimal place. And what that allows you to do is you can actually image things, like image containers, shipping containers, without opening them. So you can see what's inside something based on how it responds to gravity and figure out how much mass is in there. You can tell all sorts of things without opening it up. So that's just one of many, 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 many applications. That's the interferometer. And well, would you look at that? That's the chapter. So we only literally have one more chapter for the course, and we have 2 more lecture periods, both this week and next week. So the 4th, I am going to officially make that a review. So that will be I'll just at the normal time, we'll do that for a final review. So I got to put up a practice exam. I'm going to do that. I'll put up a review for you. That's got to be a this weekend thing because I'm behind on a few things. Extra credit labs will come out. I'm going to stop the recording here though.